Okay, this is part two of the Mother Liquor Lecture, otherwise known as the Experimental Synthetic Organic Chemistry Lecture. Quick scroll through. We talked about philosophy, planning the experiment, how to run things in parallel, emphasizing micro scale, what vessels to use, how to do inert atmosphere, bag those balloons, how to purify reagents, how to think about when not to purify reagents, stuff like that, how to measure samples, how to not use dropping funnels, syringe pumps, etc., etc., etc. Let's get to the most important part here, or one of the more important parts, and that is monitoring the reaction. I'm going to try to finish this lecture in this second swath. It's going to be a little longer than the next. Hope I don't time out. Monitoring the reaction. You always monitor reactions from start to finish. I do not care if you look at the literature procedure and it tells you what temperature to boil it at and for how long to boil it. It seems very specific. The person who wrote that procedure might not only be a grad student who might have his head up his ass, but might also be an advisor who wrote the experimental prep and modified it and did various things and took some liberties because the first rough draft was so poor and the student didn't bother to correct it. So you always monitor a reaction. Which reactions? New and untested reactions, of course you do. Reactions you personally have done before, yes, you always do. Why? Because if it fails, you want to see it fail and know where it failed. There is nothing more nightmarish than doing a reaction you've done before and then finding out that it didn't work, because then when it comes time to do it the next time, you don't know whether to scale it down for fear it'll fail or whether to scale it up and hope to not get your butt kicked again. And so you really, really want to keep your finger on the pulse of all reactions. Literature procedures, like I said, I don't care if someone did it before and it looks like an organic reactions prep. I don't care. You monitor it. You even monitor formation of transiently stable reactive intermediates. So let's say you do a reaction where you hit cyclohexanone with a strong base and you generate the enolate, and then you're going to alkylate it with some alkylating agent. And if you're following this reaction by TLC, which we'll talk about, you might, if you spot the enolate on the TLC plate, you might see all sorts of crazy crap. You go, well, that's because I spotted an enolate on a TLC plate. But if after you add the alkylating agent, you see all sorts of crazy crap again, that's the same crazy crap, then the conclusion will be is your enolate went to crazy crap before you even added the alkylating agent. And if there's a new spot after adding the alkylating agent, you go, that apparently is the one I want. So you want to monitor it. So you monitor all reactions. You walk in my office and you tell me you didn't monitor a reaction, that's the quickest way to get your ass chewed out. I am not prone to chewing asses out, but if you come into my office, I say, what did the TLC look like? You better fib or something, because I don't want to hear that you didn't follow it. Okay, when? Before the last reagent is added is always a good time. Let's see what all the goulash looks like before you add that final reagent to get the whole thing going. Immediately after the last reagent is added, sometimes something will happen very quickly. I saw a transitory spot, and then it went away, and then I isolated the wrong stuff, and I finally found a way to get that transitory spot to stay, and that was the desired compound. So you do it immediately after. So the second you inject the last reagent, you spot it on the TLC plate, you elute it. If it's a tricky reaction, you really want to know what's happening fast, then you spot it again in 30 seconds, even if you're not done eluting the TLC plate from the first. Just get the data. You can always throw those TLC plates away. I would say no more than 2 minutes after it starts, and then if nothing's happening, you can wait maybe a factor of 3 or 5. Nothing's happening, you can, a couple hours, nothing's happening, and then you might start heating it, who knows, but you can keep expanding maybe by a factor of 3 the intervals between when you react, when you start it and how you monitor it. But don't stop monitoring it. TLC is your friend. Some people use in modern era a lot of HPLC. Seems like overkill to me. I'd use TLC, but that's because I don't have some super duper Pfizer Merck quality highly automated HPLC system. And right before you work up the reaction, that's absolutely critical. You walk in, you ran overnight. Don't forget to do the TLC. What if something happened overnight? What if there was some backflow of some gas into your line? Who knows? Check it before you quench it. And then after you quench it or after you work it up, check it again. Did the workup do any damage to the thing? These are all 20-second things that'll save you tremendous amounts of pain and allow you to solve problems that you wouldn't have otherwise solved. So how do you do this? Well, you can use a large gauge needle or a gas adapter and thread a capillary tube down into it. But I'm a big fan of just, with a positive flow, just of argon or nitrogen, just pop in the joint and jam the capillary tube in. Bear in mind that if it's a TLC on something minus 78, things can happen in that capillary tube as it warms. You just keep that in the back of your head. And so if you TLC and it looks like it's working and then you work it up and nothing happened, you go, oh, maybe it warmed in my capillary tube. So then you get a little smarter about it. And if you get desperate, like I can imagine scenarios where if you do something like a Grignard, right, you get this big splooge at the bottom of the plate. And the TLC just isn't working, take out a small aliquot of the stuff and squirt it into a small vial and do a little mini workup, and I'll show you how to do that in a minute. And then TLC that, and get all those magnesium sulfate gunk out of there. Find a way to get that data. Okay, so I've been emphasizing TLC, and here's the formal TLC section. There's where the heck is it? There's a YouTube down here on doing, why does that look like, I'm positive I put a YouTube on doing TLC, but it looks like it's in there where the IR. In any event, there's YouTubes on doing TLC. How's that? There's YouTubes on doing TLC. Go find one if that one's not the right one. And so you need a little developing chamber, and you down here you make a line on your plate. You maybe a little more starting material, and then the reaction goes, and maybe some key reagents you can put there if you know it's going to show up on the TLC plate, and then you put it in the developing chamber. I'm going to assume you guys have all done this, so I'm not going to go into great detail. We get our TLC plates from Merck. You get these diamond tip cutters from, you can get them from Aldrich, but they're expensive as hell. So you just go on Amazon, you get a half a dozen for a few bucks. It's dirt cheap. And so what solvent system? That's a fascinating question. What I think you should do is have a solvent system that you like and you use routinely. And the one that we used all the time was ethyl acetate and hexane. So you use varying degrees of ethyl acetate and hexane, whether the thing pure ethyl acetate if it's super polar, and if it's super grease, you might go all the way down to pure hexane. The reason you pick one and you stick with it is because you get familiar with it. And you start to notice that if you make a mesylate of a secondary alcohol, the mesolate's really close to the alcohol and you know where to look. And if you make a mesylate of a primary alcohol, it'll go up the plate, et cetera, et cetera. You learn what the solvent acts like, and you get a sense for how polar you need to start looking. And so it just becomes like wearing an old pair of shoes. Now, you use other solvents. This is the thing I would say I blew in grad school. I was wedded to ethyl acetate hexane. And I kind of had this view that you get the RF right and that's your resolution. But different solvents really do separate different compounds differently. And so if you've got a tight separation, instead of suffering and squinting at the TLC and suffering through the flash, and vary it a little bit and see if maybe you get a much better separation with another solvent pair. I didn't do enough of that, I must confess. Very low polarity compounds, instead of adding 0.5% ethyl acetate, instead you might use ether, which is it's easier to measure out. You might use 2% ether instead of 0.5% ethyl acetate. So for really non-polar compounds that need a little polar additive, diethyl ether is fine. For super polar things, methanol and acetone, you're getting up there pretty high. If you TLC in amine, you'll get a lot of streakiness. You add 0.5%, or in a quick and dirty, couple of drops of triethylamine to the tank, and to the TLC tank, and ultimately to your flash column too. And what that'll do is it'll knock out all the acidic sites on your plate, and it'll cut the streakiness. If you're TLCing acid, you add a drop or two of acetic acid, same thing. We recently were making triamines and did a lot of Googling to ultimately try to figure out how to chromatograph triamines, and it turns out that the alkaloid chemists are all giggling now because they knew this already. But 10% aqueous ammonia, methanol, methylene chloride mixtures do a great job, and it's remarkably good. And I never knew about that until about 2 years ago, because I never had to do triamine alkaloid chemistry. There's a rule of thumb is that for every nitrogen in your molecule, you can add a year on your PhD. And nitrogens cause pain. Visualization. So you run a TLC. How do you visualize it? Well, there's a sequence of events, and this is really important. It is very important to recognize what's quantitative. What is it that tells you how much compound is there, and what is not quantitative? So, for example, right here, UV, the plates are loaded with a special indicator. So if the compound absorbs UV, you get this serious UV activity on the plate, and you can see it beautifully. It has terrible correlations with quantity, because a benzyl ether will be really weak and a benzoate ester will be really strong. So in a student, if you go diving for what you think are important compounds, you start staring at important compounds because it's strongly UV active, you're dreaming. On the other hand, if you do an oxidation or you're doing a esterification, there's a new spot and it's a benzoate ester, you better see a bright UV activity. Now, you want to know how much is on that plate, you spot enough and you run the plate, you run the TLC up the plate, and then you dry it off, and then you hold it up to a bright light and you look through the plate. And wherever you see a smudge, that's a smudge, much the way you see a smudge when you're eating a piece of pizza and the grease drops on your shirt. You see the smudge on the plate. That's the major compound. I don't care what the stains tell you. I don't care what the UV tell you. That smudge is where the compound is. Now, the spray that I used to like, and I still like it, but it requires dedication, a part of a hood, because it's kind of junky, is Jones spray, and this is the formula. But it acted quantitative. And so you spray it on the plate, you put it on a heating plate, and it stains. Very few compounds deceived me with that. So when a major compound usually showed up as a major charring. There's others. There's tons of indicators, and the problem I have is not with seeing spots. The problem is many of these show too much stuff. Many of these show things that are just phantoms. That's why I like the Jones spray. It really tends to show them in proportion to their quantity, and so you don't go chasing stupid stains of stupid things. Okay, caution, warming in the capillary. If it's a minus 78 degree reaction, you could trick yourself. Decomposition on the plate. If you TLC anything, you might get crap, which as soon as you throw in the alkylating agent, all those extra spots may go away, and that tells you the alkylation went. Notebook record. Now, here's the deal with the notebook. I'm too old for an electronic notebook. We do a lot of stuff electronically, but we don't formally have electronic notebooks. I sure as hell wouldn't start my young career now without using electronic notebooks. I'd find a good one. I don't know what the best ones are, but I would do a lot of fishing, because once you commit to it, I think you've committed in a serious way. And these are notebooks where you can upload NMRs and link to things, and they'll have Excel spreadsheets in them for calculating reagent quantities, all sorts of cool stuff, and find out which ones have the right bells and whistles and which ones don't. I actually think you should put a full-scale drawing with an accurate shading. Now, you iPhone crowd could actually do it very differently. You could just take a photograph and drag that picture. That would be fine. But I think you ought to show a depiction of the TLC plate. If you look at my PhD thesis, I replicated all the TLC plates. If you gave me an experimental procedure and said, replicate this procedure, and you get one piece of analytical data, it wouldn't be a proton NMR, C13, or an IR or anything. It would be a TLC plate. I would love to see what the original TLC plate of a successful reaction looks like, because then what you'll have here is it'll say, okay, look, here's this known compound, here's this known compound, and this will show you what you're looking for, and it'll tell you which one is the right one, et cetera, et cetera. So somehow I think you ought to replicate it. Do not, if you're using a hardbound notebook, paste TLC plates in the book. Don't do anything like that. You'll just end up with a bunch of dust in your notebook. People used to do that all the time. It was really stupid. When I visualize, so the first thing when you visualize, you got to visualize for the thing by sight, which one's the major, and I'll put a little mark, a check or something next to it, just so I don't lose track. Then you look by UV, and I put a dotted line around the UV active spot, and you want to be careful, because what you might find is that that you see a UV activity and you see a stain, and they're right on top of each other, and you say there's a good chance that UV activity and the stain are from the same compound. If they're offset a little bit, it's quite possible you've got a UV active compound that's real close in RF, but it's not the major molecule, and it's not the thing that's staining. And so you really want to sort of make sure you see that the stain and the UV correlate or don't. Note any color oddities. Tertiary alcohols with Jones spray, for example, when you first heat them to dry the Jones spray, you put them on a hot plate, they turn red because they form chromate esters that can't decompose right away. So you get a chromate ester you see on the plate, and then it chars. So if I know I'm trying to make a tertiary alcohol, I'll watch for that red show. There's different stains that show all sorts of things, stains that show aldehydes and who knows what other stains. I didn't get deep into stains in grad school. And then you also want to indicate purified sample. So if you have NMR spectra recorded on the two spots, give them compound numbers and somehow show which one represents which spectra. Now, what are the other methods of monitoring? I said you got to monitor them. TLC may not be the right one. Well, there's others. And so, for example, gas chromatography. Now, here's an important thing about GC. And one time I used to give short courses on kinetics and pharma. And I thought maybe I was telling these guys stuff that they knew, and it seemed really stupid. So one night at dinner after one of the first ones, I'm talking to the head of process, and she said, somehow the topic of using internal standards. And she said, oh my God, I'm glad you said that. I can't get anyone to do it. So you'd be surprised at what gets omitted. So here's the deal. If you watch loss of starting material and formation of product, they will correlate. They will correlate sort of. They don't have to correlate, but you can deceive yourself, because it could be the starting material goes away and the product forms in the GC, and it could be you're sending 80% of your material to crap. And if you're doing that, then you're going to have a mass balance problem. Now, if in your sample, which you put right into the reaction vessel if you want, a little dab of decane or something that's innocuous, then if you're monitoring a reaction by GC, the decane's not going to move. It's always going to be there, and it's not going to get partitioned anyway. And so what happens is you'll see the starting material go away relative to the decane and the product form relative to the decane, and you'll be able to show that there's no mass loss anywhere. It's not going to other stuff that's not showing up in the GC. You should always use internal standards. You can do kinetics with the internal standards. You can plot. You can get rate constants off it with the internal standards. It works really well. Now, there's other ones. NMR, for example. You can do sealed tube, which I emphasize is really important to organometallic guys. I think the organic guys tend not to do it, but they should. Now, the other beauty of NMR is you got all these different nuclei. So if you use proton, you got a problem where you've got hexane and stuff like that, and you might have a lot of gunk in that flask. There are times where you can solve that problem by using, instead of pentane, use cyclopentane. Now it's a singlet. There are tricks you can do. And cyclopentane is a great solvent, by the way. But you also have orthogonal solvents. So we'll occasionally deuterate a compound so that we'll be able to follow the deuterium NMR. and there's only one, right? And so all the rest of that spinach on the molecules are relevant. It doesn't clog up your spectrum. You just watch the deuterium of the starting material go away and the deuterium of the product appear. Boron 11 NMR I have in there, but boron stinks. Boron's been lousy for us. We did some boron NMR through the years, but it's not very good. Fluorine NMR is super duper duper. Fluorine is a great tag. If I went back in a time machine and was asked, what do I do in synthesis to change the way synthesis is done, I'd fluorinate every protecting group. I wouldn't use benzyl ethers or bomb ethers. I'd use parafluorobenzyl ethers and parafluorobomb ethers just to put a fluorine tag. I'd always put in a fluorine tag. Whenever we're thinking about substrates and mechanistic studies, I'm always saying, where can I fluorinate this thing just to be able to follow it? Now, my newest favorite is something fluorine perturbs molecules. Silicon, on the other hand, is not only a relatively innocuous thing and relatively inert. TMS groups are very inert, but also it's spectroscopically, it's a 5-minute spectrum. And people have, TIPS protected ethers and various T-butyl dimethyl ethers. And so there's very few syntheses that don't have TMS groups. I was just watching a Phil Barron lecture this morning, actually, and he was talking about, putting TMS groups on arenes to block sites that you don't want to go to and stuff like that. So most synthetic chemists don't even notice they have silicons all over their designs. And they should be doing silicon NMRs all the time. And we've done kind of a deep dive on silicon NMR, and the synthetic chemists are not doing it. And that should change. Now, the last one is React IR that I want to talk about. There's others. People monitor things like, calorimetry, which I'm one of my least favorites because you don't know where heat came from. It's just heat. React IR, the first React IR I ever saw was not called a React IR. It was at Lilly. It was $500,000. But when I was an undergrad, I followed a reaction by IR just for hoots. No one told me to do it. It's just a whim on my part. And I watched a rearrangement go that explained why I got a byproduct. It was really kind of cool. And so IR became a friend. When we made Monensin, it was so complicated that infrared was critical. And so again, wedded to IR. So we started doing kinetics. The first thing I did is took an IR setup, and I set up a flow system and monitored kinetics using IR. We tried to build rapid inject IR, and that was $50,000 down the drain, and my engineer sucked. And then one day I was at Merck, and I saw the first generation of React IR, and I said, I got to get me one of those. So I called the company. I went down, flew down to Maryland, and sat there with the CEO and the vice president and the venture capitalist and the inventor of the DICOMP probe. And what I told him is your React IR is great, but you needed a factor of 40. And I do have a point here, and that is you needed a factor of 40 to do the kind of kinetics we wanted to do. And they found me the factor of 40. And how do you do it? Well, if you look at this picture of our React IR compared to your React IR, the first thing you'll notice is the probe is short. It's a little snub-nosed probe. It's a 1-inch diameter probe, which means it's a 30-bounce silicon wafer. It's also not the DICOMP probe, which has a big, huge splotch right in the middle of the carbonyl region. Of course, who cares about carbonyls? We all care about carbonyls. And so by avoiding the DICOMP, which is their favorite, ASI, Mettler loves the DICOMP probe. It somehow is their baby. But the silicon probe is about 10-fold better. The 1-inch probe is about 6-fold better. So they got us the sensitivity. Now, here's the problem. If you buy a React IR from these guys, they're not going to sell you the 30-bounce silicon probe. They're not even going to think of it. You got to nag them. And then they'll say, yeah, we could do that if you want. I'd send them the design that I still have. They still make them, I think, and some of my students in industry still order them. But the gist is that we can do kinetics on 4,000 molar solutions in that probe. And this thing is, this container here is just a Teflon O-ring adapter that slips over the probe. We do 5-10 mil reactions down in here and do kinetics. And now, what they're really going to try to sell you is fiber optics, because that's their new favorite thing. And my understanding, you should ask them, but what you should do before you buy one of these things is send them a sample and say, get me a spectrum on this. I want to see your specs, because I think that I think the fiber optic probes have terrible sensitivity problems. And, pharma guys don't care. They're working at 1 molar. But if you're working in academia, you don't want to be working 1 molar necessarily. Okay, so that's monitoring a reaction. Always monitor reaction. Do whatever you have to do to monitor that reaction. I'd be shocked if any synthetic chemistry advisors didn't agree with that one. The workup. Okay, round bottom flask. Reactions, tedious, glassware intensive. Let me describe what you do. You have a reaction around bottom flask. You quench it. Next thing you know, you pour it into a SEP funnel, and then you add some extraction solvent. You shake the SEP funnel, and you drain off the organic, or you drain off the aqueous, then drain off the organic. And so now and then you extract 3 times, and then you take the organic and you add drying agent, and you filter it through fluted filter paper in a funnel, and then you put it in another round bottom flask, and you put it on the rotovap, and about 30 minutes later it's done rotovapping. That is a lot of work. It's a lot of glassware to clean. Okay, now we're going to solve that problem for you. So here's what you do, is you do the Kimball vials. Remember, did I show you those vessels? Yes, I did. I know I did. Here's the Kimball vials, right? Come on, dude, right there. I don't care if you use Kimball vials or some facsimile of Kimball vials or something, but you want to use those guys. And here's what you do. Imagine you're running a reaction. It's in a goddamn ice bath. It comes time to quench it. What do? You take a pipette and you squirt in a quench. Now you've got two layers. You've got the aqueous layer and the organic layer. You put an NMR cap back on it. You shake it. You let the layers separate. You go in with a pipette. You pipette off the organic layer and you shove it through, where the heck is that thing? You shove it through some sodium sulfate that's a plug in a pipette. And it goes right into the collection flask through the sodium sulfate. You want to do another extraction, do another pipette from the Kimball vial, and then you shove it through that plug again, and now you take out, you take the pipette out, you throw the pipette away. You clean the Kimball vial. The entire you throw the entire workup, including cleaning, will take you maybe 2 minutes. And that's how you beat the big scale. And if I can do a workup in 2 minutes that you're spending 45 minutes to an hour, I win, you lose. That's the bottom line. Okay, so that's why. And if you don't quite understand it, go back through this part of the lecture again and you listen to that again, because you do the entire workup. You use a pipette to do the drying. You don't use any fluted filter papers. You don't do any of that crap. It's all done. It's so fast. It's so efficient. That's how, for example, you'd run 10 reactions in parallel and work up all 10 in about 20 minutes max. And then you have the products. And then you put it on the rotovap. If it's small scale, the rotovap takes you about, 2 minutes. It's not something you have to go to lunch and wait for the rotovap to do it. Now, what are some of the advantages? Well, so what if you get an emulsion, right? If you do some aqueous-based workup with methylene chloride and you're not paying attention, you get an emulsion. You just throw the Kimball vial in a laptop centrifuge. This is not the ones we use. I grabbed this off the internet. But you put it in a centrifuge, in about 20 seconds of spinning. You don't even have to let it get up to full speed, and you turn it back off, and you'll have 2 layers, perfect layers from a god-awful emulsion. Now, let's say you do a workup. You know those workups where you end up with some powdery crap or some cake of stuff, and it's just, you got all these salts, and it's just a mush. Well, what you do is you take one of those and you run that into a centrifuge, and you take all that mush and you spin it down to a cake in the bottom, and then you pipette off the nice clean organic layer on top. And so it's just again, it's a couple minutes workup, even if it's a nasty workup, and then you, again, if you have to, you filter it through sodium sulfate, blah blah blah. Now here's see this flask right here, which has, we'll pretend this is sodium sulfate. It's probably something else, but so here's your Kimball vial. You're just pipetting into this a couple times from an extractive workup. You put your fingers on this, you shake it. That's how you do it. Now, this thing should have 2 things. One is that, and it doesn't seem to have it in this picture, but it should have a copper wire with a hook on it so that you can hang it off a couple of things. One is you can hang it off a scale so you can weigh it. The second thing is so you can hang it off your monkey bar so that your monkey bars become all cluttered with pear-shaped flasks. Now, the other thing is inside on the ground glass joint, you should tear the thing. So you weigh it on a scale, you tear it, and with a pencil, you write the tear on the inside of the flask. It is staggering how long that pencil tear will last, months, and it won't wash away unless you do some bizarro super cleaning job, which I don't know why you would do. Why do you have to send every flask through every cleaning solution imaginable? Totally beyond me. But the tear, so if you have all your pear shapes with hooks, then you weigh it, you got the tear, you know how many milligrams you got, you don't have to do any transferring because you forgot to put a tear, you don't have to use a cork ring and tear that or anything stupid like that. And so have all your collecting flasks with copper hooks and with tears on the ground glass part of the joint. And then you rotovap it to dry. So you always got a pump on it unless you think it's going to go away on you, so it's volatile. And then you clean the reaction vessel. What? It's a Kimball vial. You just rinse some water and squirt in some acetone and get the flea out of there and let them air dry or put them in the oven or whatever. And by the way, those Kimball vials cost about 10 cents. Again, there's all sorts of vials that this would work with. I just happen to grow up on Kimball vials. You observe and smell the sample. Now, if you are a microscale person, you will reach a point where you'll look at some small pear-shaped flask and you'll be able to squint. You'll be able to easily see a milligram. You get so good at seeing, saying, "Oh, look, I got quite a bit. There's a good milligram in there." Now, if you've never done small scale, you go, "Oh my God, I can't work on that scale." You lose mass due to percentages. You don't lose it due to grams. And so, if you're supposed to get a milligram and you lose 10% of your material, you got 9/10 of a milligram. It doesn't matter. And then you just add your deuterochloroform to that and put it in an NMR tube and go take a proton NMR spectrum if you want. Now, what about water soluble? This is so disturbing. This goddamn one, I was going to put this for the Chem 301 kids. I think I'm going to do that. I think I'm going to upload yours. You check the goddamn, the one I upload online, and there should be links showing you a continuous extraction. And there's two kinds. There's one where this is for compounds that are water soluble, and therefore they want to stay in the water. And so you these really elaborate piece of glassware to just constantly extract and extract and extract, and it's very complicated. And water soluble compounds are a nightmare. Now there's an alternative protocol, which we've done, and it worked beautifully. And I got it from Bruce Lipschitz. I said, "Bruce, you should publish this as a JOC note." I don't know if he ever did, but he should get full credit. Maybe he got it from someone. I don't know. We call it diaper chromatography. If you take the stuffing out of a diaper. Now, I found a link online where a lady said, "How much piss does that diaper hold?" My God, right? This is obviously a mother of children. And so she did the experiment. A diaper holds 40 ounces of water. That is so much water. So here's what you do. You buy some diapers from Walmart or Target, and you take a flash chromatography column and you stuff a bunch of this diaper material in the column. And then you take, instead of trying to extract out of the aqueous layer, you just pour the aqueous layer onto the diaper and elute with acetone. The acetone carries the organic off the column and leaves the water. And by that math, you can take out 100 grams of water in a decent sized flash column trivially. And anyone who's changed a diaper knows how effective they are. So in any event, so as you're going through these workups, you keep track of the mass balance. You don't want to find out you got a lousy yield after purification and not knowing if you lost on the column or in the workup or whatever. So when you get the crude, you should have a pretty good weight. Crude yields mean nothing. They've got crap in them, but you do not want a crude yield that's 50%. That means you are in trouble already. So you want to weigh crude products to make sure you don't have a serious mass loss. That would tell you, for example, maybe the compound's water soluble, or that you destroyed it, or who knows what. Don't let crude reactions sit around on your bench top or in the freezer unnecessarily. I'll show you flash chromatography. If you do a flash chromatography, it should take you about 45 minutes. One time, one of Clark's grad students left a crude in a very subtle way. The kid came in the next morning and Clark had flashed it. And he said, "Oh, I just didn't want your crude to sit on your bench." That's a total beating. That kid took a beating. That's like, "Oh, I am never doing that again." So if you can flash something in 30 to 45 minutes, and if you're taking more than 30 to 45 minutes, that means you're diddling. That means you're being indecisive. You gotta, it's like that, smashing bricks with your head as some martial artist. You gotta smack those babies with your forehead. And so it should take 30 to 45 minutes. Okay, now, this is the most contentious goddamn rule in the book right here. And that is, we do this, but we do it when we know why we're doing it. But I think there's a vast amount of wasted time and resources doing crude NMRs. And everyone says, "Oh yeah," they think it's being scientifically rigorous. No, you're just wasting your time. If you're following something by TLC and you're watching it and then you work it up and you get it and the TLC looks normal, flash the damn thing. Because if you record a crude NMR spectrum, you don't want to make a major decision based on some sloppy crap in the crude NMR. And if you're going to flash it anyways, then just flash it anyways. If you think you missed something, right? If there's a minor isomer, then the next time you go back and you take the crude NMR because now you know what you're looking for. But we don't do crude NMRs unless we know what we're looking for or unless we don't know how to purify it yet. And it won't go through a flash. We got to find some. Then we'll look. But otherwise, if TLC tells you you're in good shape, just shove it through the flash column and get. Don't forget, whenever you've done a reaction for the first time, your goal is to get 1 milligram of the right stuff. That's it. Just want a small amount of the right stuff and say, aha, here's where it is. Here's the RF. Here are the resonances. I know where it is. I know how to find it. Now I got to optimize it. Okay. Now. Caution, rule number 9, skipping crude NMRs. You will have advisors who will have a total cow and they will pass kidney stones if you tell them that I told you to do that. You're welcome to tell them I think they're full of shit, but that's your choice. Okay, purification. Take every opportunity in a synthesis to purify your products during developmental stages of the synthesis. So you'll read in a paper that someone took a crude and pushed it through and they telegraphed it or telescoped it or telecommunicated it. I don't know. Maybe we can do that now. But they didn't or shouldn't have done that in the developmental stages. You really, if you can purify it, because you don't want to find out the next step fail because you had crap in your sample. Once you've done it and you say, okay, now to push serious quantities through, it turns out I'm losing material on the column, I think unnecessarily, then you push it through, you telescope it. That's fine because now you're an educated, pharma guys don't want to flash anything, but academic guys ought to flash everything in my opinion. Okay, so these multi-step one-pot sequences also, same thing. You're throwing a Hail Mary if you're trying to do multiple step one pot reactions, or you're trying to do multiple steps and just taking the group. Famous story, supposedly, I don't know, EJ. I occasionally talk to him. I'll ask him about this. Some guy went through something like 20 steps of gibberellic acid starting to bring up, and he didn't monitor anything, and he ended up with a totally unrecognizable pile of solid. Okay, so how do you learn how to do flash chromatography? Well, you go to the paper of Clark Still. Now, flash chromatography was invented by Clark Still while I was a first-year grad student, and it transformed organic chemistry. And here's the deal. A lot of people do it in all sorts of screwy ways. Clark optimized it, and you're not using his protocols. How stupid is that? So here's what you do. If you haven't done flash, you go read his paper. And this YouTube, I think, this one right here is the one, I think it's from MIT. And the girl in the YouTube says, read the paper, and that's the best advice. Now, what Clark found was that the optimum conditions was 5 to 6 inches and a flow rate of 2 inches a minute. Now, if you think you're Mr. Smarty Pants, or Mrs. Smarty Pants for that matter, Ms. Smarty Pants, or whatever pronoun Smarty Pants, and you think you're smarter, but he optimized it. He looked at the resolutions of function of these parameters, and 2 inches a minute, 5 to 6 inches. You want to make that column longer, you get broadening. Now, here's what I will tell you, is a bigger column, a diameter, will tend to get you better resolution because you won't overload the column. Okay, so what do you use flash chromatography for? Anywhere from 10 milligrams up to 20 grams. And you got to know what column size to use. If you saturate the column, it won't resolve well, so go read the paper. We flash everything that we can. Okay, column size, see the paper. Diameter, increase the length or diameter for improved resolution. I don't know why that's there. I don't believe that. Someone added that. I think one of my editors did. I believe you increase the diameter for resolution, not the length. The MIT video says, I think that's the one that says 3/10 to 4/10 RF. It is more sensitive than that. So if you use 4/10 RF, that stuff's going to rip off the column. If you go below 3/10, that stuff's going to hang onto the column. You really want to be between 3/10 and 0.35 RF, in my opinion. Don't go lower than 0.25. You'll be there for the rest of your PhD. To determine the solvent that you're going to run the flash in, since you're monitoring every reaction, you determine it while you're monitoring it. So as you're in the later stages, you're running TLCs to see what the heck's going on. Start changing the solvent to get the RF between 0.3 and 0.35. While your crude is rotovapping, you can pack your column. because you already know what you're going to do with it. Bad guesses, right? If you say, well, it's RF 0.5, but I'm going to take a guess, maybe. The more seasoned you get, the more you can get away with that, but it's a bad idea. Make the solvent you think it is. And whiskey bottles of different concentrations. Now, here's another interesting point. I see this all the time in the literature. What's going on there? Do not measure solvent compositions by ratios. Do not say 2-to-1 ethyl acetate hexane. Do not say 3-to-1 or 4-to-1, because that will get you to think in a very, very low resolution way. So if I go from 2-to-1, which is 66%, to 3-to-1, that's 75%. That's a big change. If I go from 1-to-1 to 2-to-1, that's 50% to 60%. That's a lot of change. Go by percentage. Get yourself in the habit of using percentage. So if you say 35% ethyl acetate hexane, and you think you need a little bit more polarity, you go to 37. If you're using integer values, you're going to go to the next integer, and it's going to be a big jump. So get out of the habit of using ratios and get in the habit of using percentages. It is a linear relationship rather than a nonlinear relationship. Now, packing the column, again in the video, you can watch someone pack it. I assume you're smart enough to go to the paper. We had columns that didn't have frits in them, so the filter frit in the bottom of the column, those are fancier. We just had a stopcock, and that was it. And so you had to get a plug of cotton down in the bottom. This is a trick that I really like. Clark thought of this. Maybe someone else did. But you're trying to get the cotton down in the bottom where the stopcock is, and you're stuffing it, and it's like a video game or something. You're trying to get the cotton in there, and you're poking away. And so what Clark does is a cotton applicator. So you take something like a 1/4-inch tube, which has as an insert a narrower bore rod, a glass rod. You can just see the end right here. You put the cotton swab or the glass wool swab right in the end of and this is a long thing. This might be 1 meter long if you got a long flash column. And then you jam this 1/4-inch tube right down against the stopcock in the bottom of the column, and then you push with the plunger. Now, half the population will know exactly where this design comes from, and the other half will be only marginally confused by this, but half will know exactly what this cotton applicator is mimicking. So you pack the column under pressure. Go look at the video. Do not release the pressure while it's still hot, because it'll fracture the column. Now, it fractures the column. What do? You just pack it some more, right? This is not rocket surgery. This is not high resolution stuff. You just put more pressure on it, but you got to get the column to cool, or it will crack from the expanding gases. So you keep packing, and then sample loading. What you do is you put a narrow band of solution at the top of the column. Don't put a suspension or a sludge, because then it'll slowly dissolve and you'll end up with a mess. You got to get it on the column. There's dry loading tricks for that, and I think that's also in the video. But sometimes your crude is full of garbage, and sometimes it pays to send it through a plug of silica gel into a flask and re-rotovap it to get the garbage out, so that it loads on the column smoother. So you rinse the wall several times. Usually I'm demonstrating this, but I can't do a demo. So, and you keep pushing it on the column without disturbing the top, and then you rinse the walls and you push on the column without disturbing the top, and then what happens is you elute it, right? 2 inches a minute, preset, so you know the flow rate based on your pump that you're using, and so you set it before you add your compound. And then you keep eluting till all the material's off the column. So you do not want to stop, because your compound will broaden on the column. It can decompose on the column. There's all sorts of bad things that can happen. So you want your compound to be on the column about 12 or 15 minutes max. And if you're looking up 2 hours later and you're still eluting, you're doing it wrong. Okay, it's that simple. Your column should take 12, 15 minutes. Once in a while you get hosed and something streaks off and you got to go at it again. Changing solvent to elute more polar fraction requires knowing in advance the right RF. And so do that. So how do you monitor the column? So what you do is these are the sample numbers, right? So you have a rack of test tubes. And I use the same size test tubes, the bigger ones. I use the big ones. And then depending on the size of the column dictates the altitude, the depth of the sample collection. So if it's a 10 millimeter column, I might collect a centimeter in the bottom of the column. And if it's a 50 millimeter column, I'll collect whole test tubes. And you just get a feel for it. You'll screw the pooch a few times, and then you get a feel for how big a sample. Here's the deal, is if you're collecting well, if you got the RF right and you're collecting the right sample sizes, your compound, the target compound should start coming off around 9, 10, 11, somewhere in there. That's where the sweet spot is. If it's coming off in fraction 5, too polar, or your samples are too big. If your samples are too big, you get a lot of mixed samples. So what you do is you spot as you're running the flash. Now, people use all sorts of tricks where they turn off the column and then they change test tubes and they turn it back on. That's a colossal waste of time. Just have the rack underneath the column. If it's a big wad of material going through the column, it pays to rinse the tip of the column off before you slide it over, because it can sort of elute up the outside of the column. But then you just slide it over and you say, wow, there's something that drops between the test tubes. BFD, I don't care. You'll get a 98% yield instead of a 100% yield. And you just keep moving it along. Now, what I will do, especially if it's UV active, I'll spot this TLC plate along the bottom as it's eluting. And then when I think it should be off, so let's say I collect 15 fractions and I know I want this one, and maybe this is UV active, maybe it's not, I don't know. But let's say it's UV active, keeps it simpler. I'll look for evidence that it's finished coming off. And if it's finished coming off, then if it's still coming off, if it's UV active and it's still coming off, I'll keep eluting. I won't even bother to run the plate up run the plate. Now, I've drawn the plate sideways. You do not need a lot of vertical elevation on this plate. It doesn't have to be a big long plate. It can be about an inch tall. And it turns out that what you get is you get tearing. And oftentimes I would see two compounds that I didn't notice were there because the TLC blurred together, but I get a little terracing going on, and you might see two instead of one, and you can actually see it terracing. And so then you elute it. So what do you do? Well, so you elute this plate and say, there it is. This is the one I want. Now, if you want to get a yield, you take all 5 of these fractions. If you want to get something that just gives you an NMR spectrum, you say, okay, great, I got it, it's clean and whatever. You don't have to grope for these outer fractions, right? The fractions in the end tend to have tail and crap that hit underneath and stuff. So if you get greedy out here, you'll pick up debris. And if you get greedy here, you might pick up a little of this guy that you didn't notice. And so if you want it for purity, don't get greedy. If you want it for yield, you got to get a little greedy. Now, you don't want to mix fractions. So how stupid would it be to do the flash, get the separation, and take samples 7 through 13 or 6 through 13 or whatever? That would be really dumb. And so you don't get greedy. Now, let's say there's 2 compounds really close. Let's say this sample right here. Look at that guy. This is kind of different looking. And it looks a little lower, but you're not sure. And so how do you determine if it's lower or not? And the answer is that the trick that everyone will tell you is co-spotting. They'll say, okay, so you spot one on the plate, on a long plate, spot another one on the long plate, so spot this one on a long plate and this one on a long plate, and then you might spot 2 together and see if you get 2 spots instead of 1. The problem is you can have RF separations that are trivial, and you can't see it because the co-spot just makes the spot look a little broader. So you miss it. So here's what you do. You do A, B, A, B. You take fraction 9 and 13, and you alternate. Now, if you get a little drift on your TLC and the solvent front moves along unevenly, you can't replicate this zigzag. So this zigzag jumps out. Now, if you co-spotted these 2 guys together, you would just get one big spot. But this zigzag shows you everything. So the ABAB trick is really, really good. So you do sample collection. Don't mix the samples. Cleanup. Here's the deal. There's a balancing act between not throwing away a column containing something precious and leaving your hood full of crap. And I would err on the side of risking blowing something. Now, if the compound's really precious, be careful. But if you're just tooling along and, it's just a normal day and you got your headphones on and stuff, just when you're done, clean up the damn column. Grab your samples, do it, and then clean up your column. The messy hood with the columns that have not been cleaned up are take more time out of your day than the very rare screw up where you actually threw the sample away with the column. If you're in doubt, wait, but clean up that. Don't leave all your columns in the hood full of silica gel just because you might regret it. Get over it. Get therapy. That's what you need, therapy for that one. So clean all the stuff up. Clean up the test tubes. Clean up the rack. A whole cleanup should take 2 minutes. It's just a trivial thing to do. Now, there's also a thing called pipette flash chromatography. This is actually a video about flash chromatography, but they inadvertently do what almost looks like pipette flash chromatography. What is it? Well, pipette flash chromatography is taking a pipette, where the heck is it? Taking a pipette and putting some gel in it. And then I used to take these pipettes, and I would clip them with a flame, and that would be my collection thing. And I'd have a wooden block with 1/4-inch holes drilled, and I'd have those in it. So that was my test tube rack. And I would do, where the heck are we? I'd do a flash and a pipette. Amazingly effective, actually. So, and it's very fast. And so you literally just load your compound. And what I would do is I'd pick the flash solvent, and then I'd cut the polarity in half. I'd cut the ethyl acetate concentration in half because it's a real short column. You're looking to just get kind of a cleanup, but I would get way more than I expected more often than you can imagine. And so it's really just a 1.5-inch flash column in a pipette. And again, you throw the pipette away. The cleanup's trivial. Takes you all of 3-4 minutes. I keep telling you minutes. I keep telling you the time required to do these things so that you are calibrated, so that when you look up and it's 2 hours later and you've been fiddling and diddling because you're a wimp and you're afraid to make a mistake. I was never afraid to make a mistake. I got so used to making mistakes, it was ridiculous. And so you just got to keep moving. So you elute it and then whatever. Preparative TLC. Here's a video with preparative TLC. I am not a fan of prep TLC. There's times where it works, but I always had trouble getting good recoveries off a prep plate. And I found that it had merit sometimes when a compound was streaky. But I would never do a prep TLC over a flash, even on small scale. Without a real reason. Recrystallization, of course, this is the maestro if you want to get it on scale. Every single pharmaceutical agent out there is pretty much a crystalline material, and that's so they can purify it. You get the highest possible purity. That's how you get up to 99+% purity. That's how we don't kill soccer moms with drugs. And when you go to, if you want to do a mixed solvent system, so let's say you go to recrystallize, you know that ethyl acetate hexane or methylene chloride methanol or some combo platter is the right one to crystallize it. And let's say you want to add, let's say, the more polar one to dissolve it. And so you keep adding methanol dropwise until it finally dissolves while refluxing. Put a condenser on the top so that you're not getting a drift in your composition. So if you add a mil of methanol to 10 mils of methylene chloride, you still have that ratio, and it's not leaching out of it's not distilling away from your flask. Distillation below 500 milligrams. People can do it. I would go to Prep GC, but there's not one in our building, and I'm guessing we're probably never going to get one, and it's a shame because it really is useful for grabbing usable quantities of volatile compounds. Bulb to bulb distillation, otherwise known as Kugelrohr. That can be done anywhere from 10 milligrams, even more than 5 grams, but above 5 I wouldn't bother. These things are very expensive depending on what you get. If you get the actual original Kugelrohr, and people used to say, well, it's just a goddamn coffee pot. And then all of a sudden, Alder started selling these big ones they were like rotovaps with what looked like a big coffee pot around them. And it said West Bend on the side. So it was clear they were actually using a coffee pot. But I would go, if I got that big, I'd go to short path distillation. which is above a gram or above 5 grams, somewhere in there. And you saw a short path higher up in the notes. Volatile compounds are a bitch to use on microscale. So if you got to work with a volatile, my colleague Barry Carpenter used to make deuterated stuff that you wouldn't want to make. And he had a prep GC. That's why he needed it. Okay, so you got to distill something. How do you obtain a vacuum? You can do, of course, you do it at room temperature, but vacuum is sometimes important. There's a couple of ways to do it. One is to use an aspirator, and everyone who's used aspirators has had the experience where the thing back floods the thing and you fill up your flask with water because of the pressure change, and aspirators are just awful, so I wouldn't use them in a research lab. There's a thing called a manostat. Now, Ganem had some fancy thing, cost about $5,000, that had all these on-off valves, so you could pull a full vacuum and the thing would shut on and off the vacuum. So it would pull full, but it would occasionally bleed it as the pressure needed to be adjusted by the manostat. Alternatively, this gizmo, which I'm not going to explain, but basically you embed this tube in the middle in mercury, and the level of the mercury sets the pressure. So I'll let you go read this paper, but you can get you can get to up to like 20 millimeters of mercury, higher even with this manostat, and it costs probably a couple $100 to have the glass blower make one, and you should have a couple in the lab, in my opinion. Now, there's another interesting possibility called a vein pump, and we have a bunch of these. And this thing looks like, this is real old school machinery here. This is real early design. The vein pump, you turn it on, it's a plug, you plug it in, and there's a valve right here, and you set the pressure. And what it does is it actually sets the pressure on the vacuum, the in, and the outlet. So you use the outlet to push flash chromatographies, but you also can use the inlet to do vacuum distillations down to about 20 millimeters. So it gets down to about aspirator pressure, and you can set the pressure by adjusting this valve. Now, I would put a trap in between the distillation thing, because I have filled these things with volatiles, and I don't think that's good for them. Now, I'm going to give you one last plug for something that I think is underutilized, and that's steam distillation. Steam distillation, if you've ever done one, it's because you extracted limonene out of an orange, and that's all anyone ever uses steam distillation for. I think it's a mistake. So if you do some organic workup and you got a big glob of stuff, and your compound has some volatility, but there's some goo, there's some polymer, and because of the properties, you can't extract one away from the other. You can't just heat that up and distill off the volatiles, because volatiles will all kill you, you'll char it. So what you do is you do a steam distillation. And steam distillation, you add water and it co-distills below the boiling point of water. And actually the partial pressures are additive and there's no Raoult's law problem. And it will extract all the volatiles out of the goo and leave the goo behind, and then you end up with an extraction on the other side. And so I think it's really underutilized. I can't say that how often I've seen the need for it, but I have seen the need. Very old school, but something shouldn't be forgotten. Okay, characterization. Proton NMR requires less than 1 milligram. Of course you do that. I've got a little note here. Don't use high field NMR spectrometers. Don't get wedded to an NMR spectrometer. I have no sensitivity to someone who goes down to a facility that has 5 different NMRs but is handcuffed because they only know how to use one of them. Figure out how to use all the NMRs, because there'll be students who don't know how, and that means you have walk-on access, your personal NMR spectrometer. And my group almost has a personal NMR spectrometer for exactly that reason, and that's where we do our lithium and silicon and carbon and fluorine and stuff on that spectrometer, because the other groups don't like it. And it's fine. It's a good spectrometer. It's a 500 megahertz spectrometer. And so learn how to use all the spectrometers and then go down and use them. Now, C13 NMR spectroscopy, good purity check. You count the peaks. You ask, are they the right number? No problem. Don't be cheesy when it comes. Don't be, if you have a compound that's not expensive, load up the tube. No sense in pulsing the crap out of the spectrometer when you could have just put more in. So if you want to check the purity of some reagent you distilled, why add a solvent? Just squirt the reagent in the NMR tube neat, go down, take one pulse, boom, you got a C13 NMR spectrum. Why dilute it? There's an obsession with dilution that shouldn't be there. Now, the other thing is characterizing. Don't forget heteronuclear NMR spectroscopy. Again, if you have deuteria, record it. I go to pharma companies and they'll have fluorines in almost every drug now, and they're not all recording fluorine 19 NMR. I don't understand why. That I would record a proton first, a fluorine second, a carbon third. And as I said before, I'm totally enamored with silicon NMR because many organic molecules we work with have silicon. And here's the deal. We found it to be incredibly valuable for studying sodium hexamethyldisilazide, which really got me thinking. And then I realized we published 12 JAX papers with nitrogen labeled lithium HMDS. And at no point were we smart enough to think of recording a silicon NMR. And if we had, we would have seen that the structures of the things would have correlated with the silicon-29 nitrogen-15 coupling. And we didn't know. We just never did it. I overlooked silicon NMR. We've made easy mixtures of enol ethers and not recorded silicon NMR spectra. That's all stupid. Record silicon spectra. It might require a probe. Get your spectrometer head to make the probe available. You won't regret it. It's really good. IR spectroscopy. One time I gave a cum and I said, how would you distinguish an acid from an acid chloride, and gave no credit unless you used IR. And the students thought they'd been abused. I said, look, you will never forget this lesson. IR spectroscopy is incredibly valuable. It shows you functional groups, and there are, I know of at least one PhD thesis that ended up getting retracted because the guy didn't record IR spectra that would have shown a gamma lactone rather than cyclobutanones and things like that. And so we are enamored with IR spectroscopy. We have one React IR spectrometer per group member right now in the group to calibrate you. We have a 1-to-1 ratio. And I think there's a renaissance. And when you get to pharma, these guys monitor everything, and React IR is all over the place. And I actually helped ASI set up their academic placement program, which they didn't believe there was a market for. They were disbelieving that academics would use in situ IR. And I think there's probably an estimated 10,000 React IRs in academia. Don't forget, 30 bounce, silicon probe, short probe. Don't let them screw you up with their fancy schmancy stuff. If you're going to do mechanistic work, you really care about what probe they stick you with, or you will be disappointed. Mass spectrometry. I'll tell you, it's gotten good. GC, mass spec, LCMS, the whole enchilada. At one point, it looked like it was going the way of the dodo bird because it's very user sensitive. If you just record and say, yeah, there's a peak minus whatever, and then you pretend like you have the right stuff. High-res mass spec substitutes for elemental analysis. That in itself is enough to justify mass spec. But GCMS, DARTs, they've become fantastic. Elemental analysis, I hate them. I just hate them. They are destructive, costly, painful methods to indirectly check purity. And you send it off, and you can send it off, in space-age plastic, packed to the gills, and you'll get some message back from the place that says, oh, it was broken in shipping. Bullshit. It wasn't broken in shipping. That high school kid you hired to run it broke it and blew it. Here's an admission. One time I had a compound, I kept sending it off for elemental analysis, and I had every possible nucleus recorded. We can see all the diastereotypes. We had that compound characterized from head to toe. It was a CP cobalt boro with phosphine and carbon and everything under the sun. But the elemental analysis was jumping all over the place. And the editor wouldn't take the goddamn compound. He wouldn't let me put it in the paper. I sent off 3 times, 3 different answers. I was getting pissed off. So here's what I did. I sent it off and I said, this is what I think it is. Now, I didn't tell them to cheese it, and they got it right. That's how fucked up elemental analysis is. I didn't tell them to cheat, but I got to tell you, I think they cheated on it. That's what, and it's like, screw that. I hate elemental analysis. I was happy to declare the editor. It didn't work. I didn't care, but he was just a knucklehead. So that's the cheesiest thing I ever did in chemistry, I think. Still required by some editors. They're referees who say, oh, no elemental analysis. They got to get a life. That's 1850 chemistry. It's also the people who think that are at schools that happen to have elemental analysis facilities in their department. So it's easy to take that stance. Make sure you collect all your analytical data necessary to humor thesis committees and advisors and journal editors. So you got to know what your target is. Now, here's the problem. You make all sorts of stuff that doesn't end up in print. And so if you become anal retentive and you think that every time you make a compound, you should characterize it coming and going from head to toe, you're going to waste a ton of time. So the first time you make it, just make sure you know what you got. The second time you make it, collect some more data or collect the rest of the data. Don't go out of your way to do it until you know. Now, don't forget to get the data, though. So you got to know your own rhythms. But get it. If you got a Dart mass spec, get it. It's trivial to get, so you get the mass spec. Okay, notebook documentation. I already talked about this. Get an electronic notebook. Jack style experimental. If at some point you start repeating a prep over and over and over, don't say done in the usual way in case someone wants to access your notebook. Say done in the usual way as shown in notebook 3-265, page 365. And when you're doing a prep, you know it's going to be important, write out a good Jack style experimental while it's still fresh. And again, if you use an electronic notebook, you just do copy paste anyway. So and then put in the TLC data, details of purification, blah, 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 the whole enchilada. I got to tell you, if accessing someone else's notebook is a bit of a nightmare, though. In pharma, you got to be able to do it, but that's because they're in the business. Literature procedures include the reference. Do all the stuff plus give the reference to the compound. And if you repeat a procedure, refer back to it, show TLC data. Keep it on, be accessed by a third party. Good luck with that. Not a lot of luck with those. Sample storage and disposal. Consult the authorities. It gets trickier and trickier and trickier every passing year. No compound should be stored in the refrigerator, freezer, without proper labeling. Everything needs to be labeled. And by the way, the rules say you can't just draw a structure. You're supposed to name it, and I don't know what you're supposed to do. And so we're all breaking federal laws. I don't know what to do about that. But what you shouldn't do is put a bunch of stuff in the fridge labeled fraction 1, fraction 2, fraction 3, fraction 4. You swear you won't forget about them. You will. It's like when you find that freezer burn thing of chicken in the back of the refrigerator years later, it's worthless. You have a real disposal problem, or you do midnight disposal, which you're breaking federal law. So you gotta label your compounds so you at least know what they are. Don't say, well, I'm only doing it till tomorrow morning. Put some label that at least identifies who you are. Right? But you got to label better than that. Avoid long-term storage in flasks with ground glass joints. The freezers that are filled with cork rings and pear shapes, and they're sitting there and it's starting to get frosty in there and you can't get anything out of there. It's just an unbelievable mess. Never store anything under just a septum. Just don't do it. Never, ever, ever. Those septa are for a couple hours, not days, weeks, years. Here's something we thought was a really great idea. We went looking for it, and they sell them, and these are reverse joint vials. So that's a male and a female. I don't know, seems politically incorrect to me. Maybe that's a male and a male. I'm not sure, but you get the idea. This guy inserts in that guy, and the reason that's great is so especially for glove boxes. If you make some crystalline material or something you want to store in a glove box, and your glove box has got risk, right? Glove boxes are supposed to be clean. If you're one of those groups that does chemistry in a glove box, oh my God, that's a cesspool. But even if you're not, the drivetrain can go bad. Someone can screw the pooch and open the chamber. Someone can let something go in the box. And so stuff can go bad in the box if you don't store it correctly. Now, you therefore could actually put a little dab of grease around here, and the reverse joint allows the grease to not contaminate your compound. Now that gets to the next question. Why, in the dawn of time, did they put the female joint on the flask and the male joint on everything on top of the flask? I think the male joint on the flask and the female joint on all the things on top make more sense, except for the fact that if you're doing a dropping funnel, then you're risking dropping it on the outside, I guess. So I guess it's not totally clear, but and I wouldn't bother to switch to that system because you'll be so totally out of sync with everyone else in your lab. But these are great files, and in some we have sizes that you can't buy, and so we actually had the glass blower make a bunch because they stand up nicely and they're good storage and they're reusable. Now that's it, guys. That's experimental organic chemistry according to Dave, and And I'm happy to field questions. If someone is intrigued by something and you want to send me an email, I'll try to answer you. If you're in my courses, you certainly know how to reach me. But otherwise, that's the end of experimental organic chemistry. And I'm a little link deficient. I'm not quite sure why, but I thought I had a couple links put in there. Adios. Off she goes.